welcome our second keynote speaker on stage. Thushan Ganegedara, Senior Machine Learning Engineer at TikTok and Google Developer Expert in Machine Learning.
Okay, is everyone feeling refreshed after refreshments, or are you feeling even more sleepier? Yeah, don't fall asleep. I'm going to ask questions. So in this session, it's going to be about, it's a pretty technical session. We're going to discuss whether the LLMs are actually the good assistants we need, or if they're actually really good liars. While we do this, we will unravel some of the superpowers, their blind spots, and some of the industry use cases, how you can use these LLMs for your own advantage in your organizations. But just before I start, just from a show of hands, how many of you are still studying? Okay, yep. How many of you are working in the industry? Okay, and the rest of you just saw some free food and came in? Yeah, okay. And yeah, I'm right now just here representing GDE, not the company or the employer I work for, but I started at the University of Moratuwa, and then I went to do my PhD in Australia, the University of Sydney, and then since then I've been working in Australia. So I was working at Canva, which is a software design company, visual design company in Australia, and then I'm right now working at TikTok. Another quick announcement, so there's a couple of copies from a book I wrote that I brought in. I don't know what's the plan, but they should be there somewhere, and I might ask you questions and ask the organizers to hand them over to you, and the rest should be somewhere on the table, and you can grab one when you're leaving. But just before you grab one, this is an intermediate level book. It's not for someone who's starting out with machine learning. So only if you have done some studies, undergraduate projects, deep learning, or working in the industry with the machine learning technologies, then it might be more useful for you. All right. When you look at adolescents and teenagers, they're very good at identifying good user-friendly technologies. So I usually catch the train to work, and every time I'm on the train working, there are these cool kids behind me bragging to each other about how they're using ChatGPT to fool their teachers and so on, right? While I don't endorse what they're using it for, you can't deny the fact that they have reached every single corner of the general public. There are parents who are using to teach their kids. Obviously, there are students who are using to write that essays, homework, and everything, and professional writers who use for creative purposes. And finally, what about us, right? App developers, the very people who build these technologies, our lives have been transformed by coding assistants. So this is a survey comparison between two different times. So the first one is before the ChatGPT era. This was done by Stack Overflow, and one of the questions they asked was, what do you do when you get stuck? And 90% of the people said they Google the solution. Fast forward it to 2024, and you have another survey where 75% of the people say they use a coding assistant tool daily in their workflows. So we went from 90% Googling to 75% using a coding assistant. And that's a huge transformation. And it's not that difficult to understand why this has happened, right? If you look back to what you used to do as a developer, you go through, your ultimate target is to go from a problem to a solution, right? And what you used to do with search engines is you have a problem, you break it into sub-problems, and you turn the sub-problems into keywords or search queries, and then the engine takes over. The search engine will give you the queries to the solutions, and then you put together the sub-solutions, and you come up with the final solution. And as you can see from these highlighted red boxes, the involvement of the humans is quite high in this process. When you look at coding assistants, you just naturally, you just type your question in natural language to the engine, and it just gives you the answer. And the best thing about it is that the answer doesn't have to exist somewhere on the internet, right? Based on the pre-training data these coding assistants have seen, it can actually synthesize the new answer, customized to your own problem, which you can just copy and paste, and it'll magically work in most cases. And I must confess, I use ChatGPT quite a lot on my day job. And one day, I had this interesting problem. I wanted a heuristic-based algorithm, so rule-based algorithm, to detect screenshots, chat history screenshots. And I don't think there's that many instances of people encountering this problem. So I thought this might be a really interesting problem to ask ChatGPT. When I asked ChatGPT, it gave me some algorithm. And the basic idea is that it scans each line, and it counts how many edges were in each line. And if the number of edges is greater than a certain threshold, it will count that as an active line. And you have to have at least X number of active lines in order for this to be a screenshot. My opinion is this is actually not going to work because it's actually doing the opposite of the thing it should be doing. If you have a chat history screenshot, you should be focusing on the negative space, not the edges that are caused by the text. So a better algorithm might be, look at the lines, see how many lines have this negative space more than 50% of the time, and count, make sure the number of those negative space lines is some proportion greater than some proportion of the full picture. But ChatGPT didn't get this correct at all, despite how many hints I gave. And this kind of begs the question, right? Do LLMs actually reason? Before we dive into that question, let's understand what is reasoning. I like to think of reasoning as you have some foundational knowledge, let's say the concepts about the world. You have some rules and exceptions by which either these concepts behave or interact with each other. And then you derive new knowledge using these two entities. The process by which you derive this new knowledge is the reasoning process. It might not be the most accurate one, but I think it suffices our discussion. And this is a quick video from a professor at the Arizona State University who explains their research team's experience with the ability of LLMs to reason. Hopefully this one plays. Okay, here.
So we checked GPT-4. Interestingly, it increased in accuracy. It's still nowhere near 100%, but it went from something like 0.6% to close to 30%. So you can argue that, wow, if GPT-4 is 30%, GPT-5 would be maybe 70%, and by GPT-10, you can get 150% accuracy of some sort, right? The question that we asked ourselves is, can you explain this potentially in terms of just the retrieval as against actually reasoning? If you are doing reasoning, then if I take the blocks word and change the names, things like instead of stack, I will say feast. Instead of unstack, I will say slap, something like that. So if you have any background in logic, you realize that the predicate names don't change the dynamics of the system. And so any planner which can solve the original domain can solve this with exactly the same efficiency and accuracy. You give this to GPT-4, it dies. And in fact, we wrote this paper called
So basically what they tried GPT-4 on is a problem called blocks world. The idea is you have some color-coded boxes, you have some start configuration of these boxes stacked on top of each other. You have to have that in some end configuration, which is different to the start configuration. And you have actions like stacking, unstacking, which you can change these boxes. And when you change some of the very superficial details of the problem, GPT-4 just goes bonkers and it can't solve the problem. And this is not an isolated incident either. There's another paper by Apple, which is called GSM Symbolic. They run a very interesting experiment. You have a data set called GSM 8K, which is a maths reasoning data set, benchmark data set for LLM evaluation. And you have maths problems, all sorts of. What they did was they created a template out of the problems. So they took the names and numbers and they replaced them with different names and numbers. If the LLM can solve the original problem, they must be able to do some sort of reasoning, right? But if it can do reasoning, if it changes the names, it shouldn't affect in any way to the final answer it gets. But that's not what happens. The performance varies quite significantly between different models when you do this experiment. So, for example, Gemma 9B goes from 85% to almost 60% performance differences. GPT-4o, which is a bit more resilient, nevertheless has variation, goes from 98 to 90%. So it's not really clear whether they actually can reason. And my opinion is that they do not reason yet. But their foundational knowledge is far more superior than of an average human, which makes the boundary between memorization, pattern matching, and reasoning a bit unclear. And that's usually good enough for us to solve the tasks we need. And now let's talk about how we use LLMs efficiently and cost-effectively in the organizations. This is a diagram that I got from a video by OpenAI. So you have three different main approaches. You can either use prompt engineering on an open domain model, you can use supervised fine-tuning, or you could use retrieval augmented generation. If you think about these three approaches, you can think of these in terms of a 2D plane. On one hand, you have context optimization, which goes into your model. And then on the other hand, you have the LLM optimization or the output optimization. You push or align the model to give the output in a certain format by retraining or fine-tuning your model. Prompt engineering is more about the input optimization. Supervised fine-tuning is more about the output optimization. And RAG kind of sits somewhere in the middle, depending on the actual approach you use, but it's more about the context optimization because RAG tries to bring the most relevant context into your prompt. And when you're choosing one of these approaches, you should ask three questions. Do I have a large amount of data? Do I require external or online knowledge to solve the tasks? Do I have enough training serving budget to solve the task? And depending on the answers to these three questions, the approach you should be using will be different. So let's look at prompt engineering first. If the answer is no to all the questions, prompt engineering might be a better solution to start with. In fact, it's a pretty good, like models like Gemini Pro or GPT-4o, they're very good first candidates to try on your first iteration. On the right-hand side, you can see a normal prompt that you might give to these models. And they support a very huge context window length. So they go from 32K to about 128K. You can use this space to give more detailed task descriptions, guidelines, in-context examples. So you show how to solve, what the input and answer are for a couple of examples. Use chain of thought, which gives detailed reasoning, how you arrived at those answers. And all of this usually helps the model to reach the answer more accurately. But when you're doing this, you have to keep in mind to make it a prompt engineering process, not a prompt tinkering process. What happens in prompt tinkering is that it's just a play of words at the end, right? You can just keep changing the words until you get something. But it's also very easy to lose yourself within this process for days or weeks without making actual progress if you do not make this into a science. So two things to keep in mind. You always need a golden evaluation data set, which is a high-quality data set on which you can measure the performance of your model. The other thing is using prompt engineering tools. there are these open source tools out there like LangFuse, Agenta, which will allow you to track the evolution of your prompt and also track how the performance varied on something like the golden dataset. And here I have some evidence about the prompt engineering technique. So we had some base task, and we had an F1 score on this about 0.482. When we added the in-context examples, the performance rose up from by about 7%. And then we provided a logical breakdown of the task at hand. So this task was quite a complex task with layers of reasoning, right? And if the model gets the reasoning process wrong, it's obviously going to get the wrong answer. So providing that logical breakdown of the task gave about another 14% boost on the performance. And further fine-tuning the prompt based on the golden set by providing information about edge cases or providing helpful definitions where these models had some kind of a knowledge gap, took the performance up to by 25%. And you can see how these little changes cumulatively add up to a huge margin of improvement when you're doing prompt engineering. But there's another question. Is more context always better? Just because you have a huge wide context, should you be putting as more information as you can into that context? The answer is no. So Stanford ran this interesting experiment where they had a huge corpus of documents, and when they brought these documents into the context of the model has to pick one of these contexts to find the correct answer. And they changed the position of where this document is in the context. What you can see is when you place this context in the beginning or the end, that's when you get the most performance out of the model. If you place it in the middle, it's going to get confused. And this is similar to how humans get overloaded when you provide more and more information. It doesn't necessarily correlate with performance. So prompt engineering is a good first step, but you have to make sure you use that real estate of the context window wisely, and also you have to have some kind of systematic process to evaluate what the changes you did and how those changes affected your overall performance. And now let's look at the supervised fine-tuning part. If you have large amounts of data, and if you have a training and serving budget, this is a good option. And you can see the difference between prompt engineering and SFT, right? In prompt engineering, if you have to solve a certain domain-specific problem, you have to give lots and lots of details about what you're expecting out of the model. You fine-tune it on some set of examples, and you just have to say in very short sentence, do this, and it'll just give you the output you need. So that's the benefit. And when you're using SFT, one of the things is that you need to understand where the memory bottlenecks of these large models are. So this is the memory profile of a 7 billion parameter model. The model is on the highest end GPU you can find nowadays in the market, which is an 80 GB A100. If you look at the memory usage, the parameters take about 14 gigabytes. The gradients take about 14 gigabytes because you have a gradient per each parameter, and then the optimizer states take about twice the space because if you use something like add, it has 2 numbers for each parameter. So that adds up to twice the memory. Put this all together, you're already at the maximum memory of a highest end GPU in the market. So then the question is, how do you train these models, right? In order to find the best technique, you first need to understand where the bottleneck is. So we understood that the bottleneck is the model takes too much space or memory in the GPU. If you have a single GPU and your model fits in memory, that's the best scenario you can hope for, and you will have don't have to worry about any optimizations. If you have multiple GPUs, but still your model fits in a single GPU, you can further accelerate your training with something like distributed data parallel. And then if you have a model which doesn't fit on a single GPU, then you can use a technique called fully sharded data parallel, or FSDP. What DDP does is it copies your model onto every single GPU and sends a different batch of data into each GPU in parallel. So your training time becomes 1 over n if you have n number of batches, n number of GPUs. In FSDP, what happens is it taking this a step further. So the model is sliced into small parts, and those small parts are placed on each GPU. So if you want to compute the forward pass or the backward pass, you have to communicate with the other GPUs, bring all the slices together, form the whole thing, compute the output, and discard the retrieved parts. This increases the communication between the GPUs, but it reduces the memory by so much that you can fit these really big models on more modest GPU resources. And if that doesn't work, again, you have a whole lot of optimizations, which I'm not going to talk about because I'm running out of time. And training speed. So when you use these techniques, you can see how much performance gain you get. So for example, if you don't use FSDP, you get about 2,900 seconds. Whereas if you use FSDP, you get about a 4 times or almost 5 times speed up over the model. And it's really important to understand the quality over quantity. Quality is extremely important in supervised fine-tuning. There is this famous message, like some story between some guys fine-tuned a model on their company Slack messages, right? And then the model, after they trained this, the model started replying, "I'll get back to you tomorrow," which is pretty much what you say when someone asks you a favor, right? You say, "Okay, I'm working on something, I'll get back to you on tomorrow." So unless you actually look at the data and realize that this is happening, you're going to get a very useless model. And it's not that difficult nowadays to train these models, so it only takes a few lines of code. And it's a great way to avoid the hassle of prompt engineering. Prompt engineering is very black boxy, right? Because you don't really know what's going to happen when you engineer the prompt, because you don't know much about the model. So retrieval augmented generation is a great way if you have external or online knowledge to solve the task, which is changing at time. For example, tasks like misinformation, where news comes up, as the days goes by, then it's a really great way to use for solving your problem. But I'm not going to talk about RAG because that's a topic by itself. Let's look at serving LLMs in the industry. So when you type a search query into Google these days, you get this AI overview. And if you look at the number of search queries Google processes, in a day, it adds up to about 8 billion. And theoretically, Google might have to do this for every single query, but it does not. But theoretically, it will have to. Amazon generates these summaries of customer reviews on products. Google, LinkedIn has this rewrite with AI feature where you could rewrite your LinkedIn posts. So all of these takes LLM resources. And the process in which you serve these models is you go through this process of collecting data, you train a model, you do the offline evaluations and make sure the model is working, you deploy it, and you run some A/B experiment to make sure you're not doing something crazy that affects the user experience, and then you fully launch your product. And to serve the LLMs in the actual industry or actual real-world environments, you have these libraries that have emerged over the past couple of years. One of the favorite libraries is called VLLM, which is a client-server architecture. So you send a request, and you get a response. And if you use VLLM over something like Hugging Face, for example, you're going to get about a 24% improvement over using normal Hugging Face to make your predictions. What's the magic ingredient that enables this kind of a performance? That's something called paged attention. So what they do at a high level is in an operating system, you have virtual memory, right? So when you have virtual memory in an operating system, it's never going to store everything in a contiguous block. It's going to store in fragmented spaces to save memory, and then it's going to have a page lookup table where it knows exactly where it stored these parts of memory. The problem with LLMs is that LLMs are huge, and the variables that you need to compute the attention mechanism can go up to gigabytes. And GPUs usually store this in a contiguous block, which can cause memory problems, underutilization, and effectively slow down your performance. What this one does is it stores this in fragmented way and maintains a lookup table so it knows where exactly it stored this information. So it can, make it to the GPU like it's a contiguous block virtually. And this gives the superpower for this library to serve requests at this scale. And when serving, you have the throughput and the latency. Those are the main metrics you look at. And for latency, you have something called time to first token, so how much time it takes to generate the first token, and then TPTO, which is time per token output, which is on average how much time it takes to generate a single token for an LLM. And quantization is one of the other really good practices you can incorporate to serve these models at scale. So when you quantize the models, here in the example, the model size becomes 4 gigabytes from 27 gigabytes, and the QPS goes up by twice. So that's a really straightforward way you can, if you're running into problems of serving the request as fast as you need to, then you can try quantization. Batching is another technique, which I'm not going to go into details because I'm out of time, and probably a lot of you are already falling asleep. And if you want to use VLLM, for example, on Vertex AI, it's pretty straightforward. Only takes a few lines of code, and Google already provides that ecosystem you need to serve these models quite instantly. So whoever figures out this, to serve these models as fast as they can, they're probably going to win this AI race because that's where the bottleneck is right now. So there's so much demand for these features and so little resources out there to serve these models. This is just a conclusion of all what we discussed, so I'm not going to just repeat that. And yeah, thank you. For questions, but I can take them offline if there's no time.
Thank you, Thushan, for that thought-provoking keynote. Your deep dive into the capabilities of LLMs has been both insightful and interesting, leaving us with much to ponder about the role of LLMs in the future of technology. So I'd now like to invite you back over to the stage because we have a token of appreciation ready for you. And to present Mr. Thushan Ganegedara with his token of appreciation and to say thank you, I'd now like to invite over to the stage Mr. Chamod Pereira, GDG organizer here in Sri Lanka.